Welcome back to the Tech Mechanic. Continuing our Solutions Architecture series, let's dive in. Imagine Amazon announces a massive sale and suddenly 1 million users open the website. If all requests go to a single server, that server will quickly become overloaded and may crash. So how do companies like Amazon, Netflix, and Flipkart handle millions of users? The answer is load balancing. Today we'll learn how load balancers distribute traffic and keep applications available even during massive traffic spikes. When an application is small, a single server may be enough. But as users increase, the server must handle more requests, more CPU usage, more memory consumption, and more network traffic. Eventually, the server reaches its limits. Architects know that relying on a single server creates both performance and availability risks. A simple solution is to add more servers. Instead of one server handling everything, multiple servers share the workload. This increases capacity and improves availability. But a new question appears. How do users know which server to connect to? This is where the load balancer enters the architecture. A load balancer sits between users and servers. Every incoming request first reaches the load balancer. The load balancer decides which server should handle the request. Users don't need to know how many servers exist. They simply send requests, and the load balancer distributes them intelligently. One common strategy is round robin. The first request goes to server 1. The second request goes to server 2. The third request goes to server 3. Then the cycle repeats. This ensures traffic is distributed evenly across all available servers. For many applications, this simple approach works surprisingly well. Servers sometimes fail. Hardware issues, software bugs, or maintenance activities can make a server unavailable. Load balancers continuously perform health checks to verify server availability. If a server becomes unhealthy, the load balancer automatically stops sending traffic to it. Users continue using the application without noticing any interruption. High availability is one of the biggest reasons architects use load balancers. If one server fails, other servers continue serving requests. Users experience little or no downtime. This redundancy is critical for e-commerce, banking, healthcare, and enterprise applications where availability directly impacts business success. Let's revisit our shopping application. During a festival sale, thousands of customers browse products and place orders simultaneously. The load balancer distributes requests across multiple application servers. No single server becomes overwhelmed. This allows the platform to support more users while maintaining fast response times. Architects ask a few simple questions. Do we expect high traffic? Do we need high availability? Can a single server become a bottleneck? If the answer is yes, a load balancer is usually required. Most modern cloud architectures use load balancers because scalability and reliability are fundamental business requirements. Let's summarize. A load balancer distributes traffic across multiple servers. It improves performance, supports scalability, performs health checks, and increases availability. Great architects understand that adding servers alone isn't enough. You also need an intelligent way to distribute traffic. In our next video, we'll learn about CDNs and discover how global applications deliver content quickly to users around the world.